introduction. I was surprised how you pronounce my last name exactly the way I would like it to be pronounced. Because in Russian it sounds like Lawrencenko, but it's impossible to say Lawrencenko for English-speaking people. So this way it's easier and can be easily memorized as a Lawrence and Company, Lawrencenko. It's pronounced the same way, Lawrence and Company, Lawrencenko. Also, I would like to thank the organizers of this marvelous workshop, and personally, I'm very Mikhailovich Raygorodskiy for giving me the opportunity to give a talk today. The title of my talk is, here's the address, my email address, and the address of my personal website. The title of my talk is Irreducible Triangulations of Too Many Folds with Boundary. Actually, I will say surfaces instead of too many folds. But I gave this the title to my talk because last year a very good and important paper was published in Graphs and Combinatorics with exactly the same title, Irreducible Triangulations of Too Many Folds with Boundary. I'll mention this paper later. So to deviate from that paper, the title of that paper was this, of surfaces with boundary. So I changed to Too Many Folds with Boundary to deviate from the title of that paper. We'll consider closed surfaces and also surfaces with boundary. This is a joint work with Maria Jose Chavez, Sei Ligani, Antonio Quintero, and Maria Trinidad Picha. Okay, look at this operation of contraction of an H in a triangulation. The preceding talk, Roman Karasov gave a nice talk about triangulations, and still you can see his pictures on the board. You see an H, D prime, D double prime, and the two faces attached to that H. The two faces incident with that H. And we want to contract that H. When we contract the H, D prime, D double prime, it degenerates into one single vertex V. And the two faces collapse to two single edges respectively. And the inverse operation is called splitting, vertex splitting. And we often say shrinking instead of contracting, because this is a term used by David Barnett. And when I was a graduate student at Moscow State University Department of Mathematics and Mechanics, I graduated in 1984. I was under huge influence by Barnett's work. So far I preferred the term that he used personally. He said shrinking instead of contracting. Look, suppose we want to shrink the H, D prime, D double prime in a triangulation. And here you see the two faces attached, which are incident with that H. And assume that the H, D prime, D double prime occurs in some cycle shown in red, made up of three edges. This cycle doesn't bound, the red cycle doesn't bound any face, so we call this non-facial. A non-facial cycle of three edges, or we say of length 3, is a cycle of length 3 that doesn't bound any face. Suppose that we want to shrink the H, D prime, D double prime, and see what will happen. Multiple edges occur, or parallel edges. But in a triangulation, no multiple edges are allowed. I explain why. Because in the topological graph theory, we want all our objects to be simplicial complexes. But you remember the definition of a simplicial complex. The intersection of any two simplices must be either empty or a simplex of smaller dimension. So no parallel edges can exist in a simplicial complex. So we say that this H, D prime, D double prime is unshrinkable or non-contractible. Non-contractible, because if you insist on contracting this H, it will rule you out of the class of simplicial two complexes, and also from the class of triangulations, because by a triangulation we mean an object that corresponds to a simplicial complex. So no multiple edges are allowed. here I just proved that there exists exactly one irreducible triangulation of the sphere that is a familiar tetrahedron. This is a simple fact, but I'll prove it, and meanwhile I'll introduce some important concepts. This is the result of Gigami, Sabitov, and yours sincerely, which says that each triangulation of the sphere has a vertex with the property that its star, that is the union of all the faces meeting that vertex, has no chords. A chord would be an edge which joins two points on the link of the vertex sphere, that is on the boundary of the star, but itself it doesn't belong to the star, to the boundary of the star. But this dotted red edge would be a chord. But we proved that there exists a vertex sphere that doesn't have chords at all. So, but if there were a chord like this, then we wouldn't be able to shrink the edge VU because it occurs in some non-facial cycle, you see, or we won't be able to shrink the edge V, the W, for the same reason. But because our theorem says that no chords, it means that you can shrink any edge incident with the vertex V, this, and this. And we shrink this edge and again apply our theorem looking for next shrinkable edge and shrink it again. And this way, by contracting shrinkable edges, contractible edges, sooner or later we'll reach to a triangulation of the sphere with just 4 vertices, which is a familiar tetrahedron on the sphere. This is an embedment of a complete graph of 4 vertices on the sphere. Here, actually, you can shrink any edge because again, look, you can shrink any of the edges of the tetrahedron and no parallel edges would appear. But another ugly thing would happen. Look, if you still insist on contracting an edge in this triangulation, this will give you just a cycle of length 3 made up of 3 edges embedded on the sphere, which is not a simplicial complex again, because look, it will have 2 faces, the upper hemisphere and the lower hemisphere, whose intersection is just the whole cycle of length 3 edges, which means that this is not a simplicial complex. So we must stop here, and we shouldn't shrink any more edges because it would again get us out of the class of simplicial complexes. So we stop here, and in this sense we say, that this is the only irreducible triangulation of the sphere, just K4 in the sphere. Now I give you a more accurate definition. And the edge is called a contractible. If you can contract it, and this doesn't get you out of the class of triangulations as simplicial complexes. Specifically for closed surfaces, if you have a triangulation of the closed surface, there are 2 impediments to edge contractibility. The one is that if the edge occurs in some non-facial cycle of 3 edges, you cannot contract it. I explained why. And the second reason is that you cannot contract any edge in the tetrahedral triangulation of the sphere because again it will get you out of the class of triangulation. Only 2 impediments, and pay attention on the second one applies specifically for the spherical case, and if you have a triangulation over the torus or a hygienous surface, maybe non-orientable closed surface, then actually only the first impediment will work. You cannot contract an edge only if it occurs in some non-facial cycle of length 3. And we call it triangulation irreducible if it has no contractible edges. So you can take any triangulation of a fixed closed surface and contract its edges, and contract its contractible edges one by one, and sooner or later you'll reach a triangulation which has no contractible edges, and we call such a triangulation irreducible. Okay, and it is an important theorem by David Barnett, joint work with Ederson. published in Israeli Journal of Math in 1989. They said that actually for each closed surface there exists at most finitely many irreducible triangulations, which is good news. The number of irreducible triangulations is finite for any closed surface. And of course the question occurs, so what we know about surfaces of small genus surfaces. And here is the table in which I just wrote all the results known up to date. The first line is the sphere S0 in the sphere. And as I said, I proved above that there existed precisely one irreducible triangulation, the K4 in the sphere, which is actually a simple result, and of course it was known a long time ago. This result appears in the remarkable book by Steinitz and Rademacher, published in 1934. Then look at the projective plane, N1. N1 means a projective plane, that is the sphere fitted with one cross-cap, or with fitted with one cross-cap. And there are precisely two irreducible triangulations of the projective plane. Later I'll show those triangulations. For the projective plane, obtained by Barnett in 1982, Journal of Combinatorial Theory, Series B. One of them is the embedding of the complete graph K6 in the projective plane. It is a triangulation, and another one has 7 vertices. For the torus case, actually S1, the sphere fitted with one handle, the torus S1. There are precisely 21 combinatorial types of reducible triangulation obtained by yours truly in 1987. And the number of vertices vary from 7 to 10. Here, this column shows, this column shows the smallest number of vertices in an irreducible, triangulation of the corresponding surface we can have. And here's the maximum number of vertices in an irreducible triangulation. For the Klein-Plattel M2, there are precisely 29 irreducible triangulations found by Ligami, yours truly, and Tom Sulanti. Actually, there was a little gap in our original proof with Ligami, and later that gap was filled in by Tom Sulanti. Interestingly, Tom Sulanti works for physics department of University of Indiana. But he got very interested in this mixture of the topological and combinatorial stuff. So he filled in the gap. Actually, he used basically our approach. So this result, the total of 29 irreducible triangulation of the Klein-Plattel is attributed to 3 of us. Okay, and Solanki didn't stop on the Klein-Plattel. He wrote a very efficient algorithm finding all irreducible combinatorial types of reducible triangulation of any closed surface. And here he wrote a computer program, and he found all the reducible combinatorial types of reducible triangulations of the N3, sphere with 3 virtuous bands of cross-caps, S2, the double torus, and N4. And you see how the number of the second column is the number of those irreducible triangulations, and you see how that number grows very rapidly. Solanki published most of his results in this direction on arXiv, as well as you can find his result on his personal web page, which can be easily found on the web. And it's interesting there. It's also a remarkable fact that the maximum number of vertices that an irreducible triangulation can have is big theta of chi, where chi is the Euler characteristic of the surface. And the smallest of the number of vertices is big theta or square root of chi, asymptotically. Now, so everything was done for irreducible triangulation of closed surfaces. So it seems unlikely to get, to get, uh, to, 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 uh, So people turn to the surfaces with boundary. And I think the first paper in this direction was the one I mentioned in the very beginning of my talk. The title of that paper is the Irreducible Triangulation of Surfaces with Boundary. People started considering the surfaces with a boundary, and the easiest one is once a punctured surface, which is obtained from a closed surface by the removal of a disk. For example, once a punctured sphere is again a disk topologically, and once a punctured projective plane is a Möbius band, etc. So for once a punctured surface, there are three impediments to edge contractibility. The first one is the same as before for the case of closed surfaces. You cannot contract an edge that occurs in a non-facial cycle made up of three edges. The second impediment that you cannot contract a chord, which means a non-boundary edge. You remember, in a once punctured surface there is a hole. If there is an edge which doesn't belong to the boundary, but joins to boundary vertices, then you cannot contract this edge. Why? Because of course, because it will just change the topology of the underlying space. It's obvious. And the third impediment is simple. If you have a hole length 3, that means the cycle of length 3 is the boundary of that hole. You cannot contract any of the edges for the same reason. It will change the topology. It will close the hole. And that is that paper I mentioned before in the very beginning of my talk. Nakamoto, Bulk, and Collins here. They were published in Graphs and Combinatorics last year. In particular, they proved that the finiteness of the set of irreducible triangulation of any surface, for any surface with boundary. Again, the set of irreducible triangulation is finite not only for any closed surface, but also for any surface with boundary. And let's see what specifically is known for surfaces with a boundary. Not much known up to date, but a little is known. The first line shows actually once a punctured sphere, which is a disk again. And of course, it's a trivial case. There is only one irreducible triangulation of the disk. This is just a single triangle. And let's look at the second line. N1 minus D, which means the Möbius band. It's a once punctured projective plane. It's a Möbius over that. Actually, we found all combinatorial types of irreducible triangulation of the Möbius band last year in 2013. This was a joint work with Chavez, Quintero, and Beecher. I show you the list of those triangulations shortly. And as far as the once punctured torus goes, the work is still it is not complete yet. And we have found as many as 293 irreducible triangulation of once punctured torus, but we are not sure yet that this list is complete, and we are going to complete this work in a couple of months, hopefully. And here is the list of irreducible triangulation of the Möbius band. Actually, the smallest one has 5 vertices, and the largest one has 7 vertices. To obtain a Möbius band, you should identify the left and the right sides of each rectangle in anti-parallel. That is, changing orientation as usual. You will get a Möbius band doing this. And I want to give you the idea how we got this triangulation and how we are looking for all the irreducible triangulation of once punctured torus. Sorry, I will will give you the idea, but on the example of the Möbius belt, because this case is simpler than the once punctured torus. So remember that the Möbius belt is just once a punctured projective plane. So we start with these two irreducible triangulation of the projective plane that Barnett found in 1982. The one on the left has just K6 in the projective plane, and the one on the right has several vertices. So then we, by splitting some of the vertices of these two irreducible triangulations, we obtain the list of all combinatorial types of triangulation of the projective plane with up to 8 vertices. This 8 triangulations and 12 more. There are in all 20 triangulation of the projective plane with up to 8 vertices. Notice that some of the edges are shown red and some are shown bold black. Actually, the red edges are non-contractible edges. We call them rods. It's easy to remember, each rod is red. The red edges represent rods, that is non-contractible edges. And the black edges, bold black edges, represent what we call cables, that is contractible edges. And here I would like to introduce the English word pylon. Here you can see this beautiful picture. It's an artistic photography by Catherine Hadler. Actually, a pylon in Russian means pylon, bashня, or bashня lamp. And a pylon in Hebrew sounds amud metach gavoha. Thank you, Nobel, for the Hebrew lesson that you gave yesterday in the morning after your lecture. So for mathematicians, it's important only that a pylon in a triangulation is a vertex with the property that all the cables, black edges, all the cables are incident with that vertex. If there exists such a vertex in a triangulation, we call it a pylonic vertex. And the triangulation which has a pylonic vertex is called a pylonic triangulation. And actually, our proof is based on this crucial lemma, which says that for any closed surface, if you want to obtain all irreducible triangulations of the once punched surface, once punctured surface that is obtained from S by the removal of a disk, then you need to look, you need only to remove, either to remove a vertex from an irreducible triangulation of S, or remove a pylonic vertex from a pylonic triangulation of S. Here you may be curious why I use an indefinite article A in the second way of obtaining the irreducible triangulation, because actually you know such triangulation that have only one cable. If, for example, there are known some triangulation of the torus with precisely one cable. And then it has two pylonic vertices. Either of the n points could be regarded as a pylonic vertex. But if the number of cables is 2 or greater than 2, and the triangulation has a pylonic vertex, of course it would be unique. Just in conclusion, I'll give you some examples. This is one of those irreducible triangulation of the projective plane I showed you above before. And look, here, this is a pylonic triangulation of the projective plane, because you see this vertex 6, the double prime, is a pylonic vertex. And this is a pylonic triangulation. So if we remove the vertex, this pylonic vertex 6 double prime, we'll get a hole in the place where the star of that vertex was And then we can easily redraw this. This is already a triangulation of the Lagos band, of course. And you can easily redraw it in the way that I showed you on the list of all the reducible triangulation of the Lagos band. And I think I better stop here. Thank you.
Questions?
I have a question. Well, if you have a list of some triangulations, then how you distinguish that one is not equivalent to the other? Are they distinguished by the number of vertices and triangles, or something else?
Good question. Actually, as I said, I didn't say it. You listened to my talk very attentively, because really I didn't give a definition which triangulation should be regarded the different and which should be considered the same. Actually, in this list, for example, always in this talk, I distinguish between triangulations, what we say up to isomorphism. Two triangulations are called isomorphic if there is a bijection between the vertex sets, which takes faces onto faces. You know, the automorphism, the two graphs, is a very familiar concept, graph isomorphism. Two graphs are called isomorphic if there is a bijection between the vertex sets that takes edges onto edges. Here similarly, but not edges onto edges, of course edges onto edges, but moreover faces onto faces. And the inverse bijection, of course, one must also take faces into faces. So, but in the topological terms, it would be said that two triangulations are the same from the combinatorial standpoint if they are homeomorphic in topological sense.
Okay, this is the definition, but for example, Zolonki had to distinguish 6 million.
All of them are pairwise non-isomorphic.
It was checked by some, by some brute force or some clever algorithm or whatever.
Yes, by some clever algorithm. You can find his algorithm on his personal web page. Or if you email me, I'll send you the address of that page. Yes. Can I speed up? Here. Here's my email address, Lawrencenko@hotmail.com. And here's my personal web page, which I didn't update for a long time, Lawrencenko.ru. Lawrencenko.ru.
It's not the same as graphic?
The .ru, I'm sorry. Huh?
It's not the same as graphic? Because for three connected, the faces are determined. Right?
A graph has no faces, just edges. It's one-dimensional complex. But I was talking about triangulation. The question was about triangulations.
Yeah, but for linear triangulation, the faces are determined, right?
Yes, a Whitney theorem, of course. This is a Whitney theorem that says that actually, but it's another question. We can make a more subtle the distinction between triangulation. It would be, for example, if there is a cycle U with a W in one of them which doesn't bound with the same graph. Suppose we have two triangulations of the same sort with the same graph. And if there is a cycle U with the W in the graph that bounds a face in one but not in the other, we can say that these triangulations are different. But this is a stronger way of distinction than up to isomorphism that I supposed in this talk.
All right. Any other? I mean, we saw yesterday that they don't open the door for dinner before 6:30, so no point. Okay, let's thank Serge again.